Hello everyone, myself Nish Kumar. In this video, I am going to share my internship experience at School of Computing and Electrical Engineering, IIT Mandi, under the supervision of Dr. Aditya Nigam, Chairperson and Associate Professor. The project title is Forehead Creases Verification by Detector and Detector-Free Techniques. In this presentation, I will be walking through the following sections: key concepts, work done, and then results and conclusion. Firstly, in the key concept, I explored the LOFTR, a local feature transformer. It utilized shared CNN and the attention-based mechanism. In this, we pass the pair of the grayscale images, and the pair of the grayscale images then pass through the shared CNN to obtain the dense feature map. Then the positional embedding is appended to it to preserve the spatial structure, and it then combines the self-attention and cross-attention mechanism to focus on the contextual behavior. Then it passes through the differentiable matching layer to compute the correspondence between the features. Let's see in the detail. Firstly, we pass two images, means the pair of images IA and IB, to the local feature CNN module, means CNN based architecture. It may be a simple CNN architecture or the pre-trained architecture, and it extracts the feature map of the resolution 1/8 and 1/2. Then it passes through the flatten level coarse feature transform. In this, we flatten the feature map and appended the positional encoding to preserve the spatial structure. Then it passes through the LOFTR module. In the LOFTR module, it passes through the self-attention layer and cross-attention layer. Then the output of this module is passed through the differentiable matching layer, and in the differentiable matching layer, it finds out the confidence matrix for the coarse level features. For example, if the match is found at the pixel 100,100, then in the fine level module we crop the patches around 100,100. Then in the coarse to fine module, the cropped or the fine features passed to the LOFTR module and found the correlation and apply the softmax on the output, and we will get the expectation. Next, I explored the homographic estimation. Homographic estimation is the transformation matrix that transform the view from one surface to the another. It is basically a 3 by 3 matrix with the degree of freedom 8, requiring at least 4 points of correspondence. It transforms the image to the another version. For example, if we have the image A and we apply 3 cross 3 transformation matrix on the A, then we get the wrapped version of that image, say A dash. Next, I explored the VGG16 architecture. VGG16 is the pre-trained model based on the CNN architecture. It accepts the 224 and 224 input image in the RGB format, and it has the 5 convolutional block in the pooling layer and the 3 fully connected layers. Next, I explored the vision transformer. Vision transformer is similar like the concept of the transformer that we use in the NLP, in which we tokenize the input sentence and convert into the embedding. Similarly, in case of the computer vision, uh, we divide the images into the equal size of the patches. For example, if the size of the image is 224 into 224 and the size of the patch is 16. Then we get the we get the patches of size 14 cross 14 means 196 total patches. Then these patches pass through the linear projection of the uh, flattened patches, means we multiply the weights and adding the biases. Then positional embedding is embedded position embedding is appended to the flattened patches to because the vision transformer is position invariant. Then extra learnable embedding class embedding is prepended to this position this embedding which gather the information of the whole attention contextual behavior. Then this is passed through the transformer encoder. In the transformer encoder, embedded patches are normalized, means the input to every block is normalized, having the mean 0 and the standard deviation 1. Then in the then it passes through the multi-head attention and also residual connection, residual or skip connection is there. Then it passes through the MLP head and we get the classification. The main feature of the vision transform is that it is the convolutional layer free convolution layer free method, and there is no need of the decoder because uh, and we don't need any sequence output, so there is only encoder is present in the vision transformer. Next I explored the Rensek algorithm. Rensek stands for the random sample consensus. It try to fit the model that cover the maximum of the inlier point. For example, if we consider the example of the linear regression, in the first iteration, consider the line passes through only the 2 points, and in the next iteration, it passes through three, and after number of the iteration, it passes through the 10 points, and there are a few points that are away from that line. Then we can say that this is the outliers to that fitted model. So the Rensik algorithm try to fit the model that can on the points that contain the maximum of the inlier and neglect the outliers. And these are the some of the performance matrices that I use to compare the performance of models. Firstly, SSIM, structural similarity index uh, measure. It utilizes the mean and the standard deviation and the variance, and some coefficients C and C2 are utilized to avoid the division by 0. And its interpretation is if we get the value 1, then we can say that there is the perfect similarity, and if we get the value -1, then we can say that inverse similarity. Then in the cosine similarity focus only on the direction, not only on not on magnitude. If the value of the cosine similarity is 1, then we can say that this is a similar structure or in the same direction. Next is the Euclidean distance. It find out the straight line distance between the 2 points. Lower value of the Euclidean distance specify the more similarity between the vectors or the features. Next is the ER, equal error rate. It is the value at the threshold where the false acceptance rate and the false rejection rate are equal. Lower value of this rate indicates the better classification performance or better system performance. Next is the mean corner error. A mean corner error basically find the geometrical accuracy. It find out the distance, find out the transformation, that how the corner points are shifted uh, from its exact location to another location after performing some operation. Next, I explain the work done that I have done during this internship period. In the first algorithm, I prepared the data set for training the various kind of the models. Initially, I have the data set which contain the forehead images like these images, original images, say SRC images. src is nothing but is the name given to the data set. Then I load the original image and define the corner points. Then I randomly pervert the corner with the specified range. In this, I utilize the permutation range minus 32 to plus 32 or minus 8 to plus 8. Then estimate the homography matrix using the OpenCV. There is the find homography function in the CV2 module of the Python. Then I wrap the original image to get the wrapped version of that image. And after applying this homography matrix on the source image, I will I get this image. This is the wrapped version of this original image. So I repeat these tasks continuously for all the images available in the dataset. In the next algorithm 2, it deals with the preparing the architecture of the BG16 and training the BG16. Firstly, I receive the pair grayscale images. For means I have image from dataset and the its wrapped version. Then I stack the source and destination image, load the homography matrix and flatten matrix to extract only first 8 values because the 4 points are used to compute the correspondence, and in the 3 by 3 homographic matrix last value is set to 1. Then in the model architecture, I start with the pre-trained architecture of VGG. Then I modify the first convolution layer of the VGG16 because the VGG16 original architecture of VGG16 accept the input in the RGB format, but I have the input input images in the grayscale, and its channel is 1, and I have 2 images, but the VGG16 by default accept only the 1 image. Then I stack the image and convert it to the 2 channel and pass it through the convolutional layer. And first convolution layer, I modify the first convolution layer to accept 2 channel. Then keep rest of the convolution layer as it is and freeze all the layer except the selected layer. I freeze and I keep the layers trainable that are in the last block of the convolution block. Then extract the feature to the 5 1 to channel tensor and pass through the regress. And this is the fully connected layers. And output of this is the predicted homographic parameter. Then in the training setup, for each epoch and each batch in the training data set, there is a forward pass where the model predicts the homography, compute the loss. In this task, I utilize smooth L1 loss. It is the combination of the mean squared error and the mean absolute error. Then I apply the back propagation and update the weights, compute the corner error. And this task is continuously going on, and model is evaluated on the validation set, and I save the best model if the validation loss improves. Then for the evaluation phase, I load the best checkpoints, and for each batch in the test set, I predict the homography, compute L1 loss, smooth L1 loss, and corner error. And in last, I report the average test loss and the test corner error. Similarly, in case of the algorithm 3, instead of the 16, I uses the pre-trained architecture of the vision transformer VIT. In this, all things are the same except the uh, model architecture. In this, I also modify the first embedding layer to accept the 2 channel input, then then freeze all the encoder layer except the layer 2nd, 6th, 8th, and 11th. Then output feature vector is of size 768, and then pass it through the uh, regressor head, and it utilize the ReLU activation and linear layers. Then in the training setup, I repeated the same task that I have explained in the algorithm 2, and the evaluation phase same task. And in last week, I get the average test loss and the average corner error. And this is the result of the algorithm 2, in which I trained the VG16 model on the both data set that I have generated using the permutation plus from minus 32 to plus 32 and minus 8 to plus 8. In the data set that I have wrapped using the minus 32 to plus 32 permutation, I get the test loss 0.90 and the average corner error 2.07. And in case of the model trained on the data set that is wrapped with the permutation plus minus 8, average test loss is 0.15 and the average test corner error is 0.50, which is quite better than the earlier result. And this is the result of the algorithm 3. Algorithm 3 is the vision transformer architecture and training, and in this I get the test loss 0.10 and the average corner error 0.36, which is more better than the VG16 test results. Then in the algorithm 4, I generated the score file by using the trained VG16 and the VIT. For the score generation, I utilize the embedding of the image pairs to compute the Euclidean distance and predict homography matrix to compute the structural similarity index measure and the cosine similarity. For making the pair, what I have done, I initialize the empty score list. Then for each test image, I extract the identity of the test image, and then for each train image, I also extract the identity of that train image. Then I pair the each test image with the every train image available in the train set, and set the label 1 if the identity of both the images. For example, if the image in the test data set belong to the subject A and the image in the train set also belong to the subject A, then we can say that it is the genuine pair, or its label is 1. Then I stack the test and the train images as a model input, and I pass this input to the model to predict the homography matrix using the model. Then I pass this pair to the I pass the train with the wrapped version of the images and pass through the model and get the embedding for that image pairs. And for the for computing the Euclidean distance, I uses the embedding of for image pair, and the for cosine similarity and the SSIM, I use the predicted homography matrix. And then in last, I normalize the score in the specified range from 0 to 1. This is the result of the algorithm 4, where we can see that the genuine and imposture is the label of the image. Uh, if the image belongs to this subject 1, and image belong to the subject 1 in the train, then we set its label is 1, otherwise 0. And this is the structural similarity index measure and the cosine score. This is the Euclidean distance, normalized Euclidean distance computed by the VGG16 on trained on the REP data set generated by the permutation minus 8 to plus 8, and this is the normalized Euclidean distance from test to train pair using the embedding of the VIT. Next is algorithm. In next algorithm, I prepare the new data set. I have the collection of the videos and some of the extracted frames. Then for each video, I extract the frame at each interval, and for each frame, I visually inspect the forehead creases. If the crease is clearly visible, then I save the frame with the clear crease, otherwise neglecting this frame. Then the filtered images are uploaded to the RoboFlow. RoboFlow is a tool for uh, annotation or generating the annotated data set with in different kind of the formats like YOLO format, CSV format, etc. Then in the RoboFlow, I draw the forehead bounding boxes on the forehead of the images and export the bounding box label in the YOLO format. Then annotated image and labels, I pass the bounding box coordinates and crop the forehead region from the images and save the cropped forehead image. This is the results of this algorithm. For this example, initially I have extracted frames like this and desired forehead images. After annotation, I get this image. Next, in algorithm 6, I use the pre-trained version of the LOFTR. In the LOFTR, what I have done, firstly I resize all the images and convert it to the gray scale if not, and normalize the pixel value, convert to PyTorch tensor, and move these tensors to the GPU. Then I create the input dictionary and run the pre-trained LOFTR module. In the LOFTR module, I extract the key points, means uh, the points in the image 1 and the points in the image 2 that matches with each other, and also extracting the confidence score. And this is the result of this algorithm. I have the image 0 and src.jpg and 0 dst.jpg. This is the images from the REF dataset, and I will get this coordinate x0 by 0 in the image 0 and x1 by 1 in the image 1 with this confidence. In the algorithm 7, uh, what I have done, I have the actual image and the wrapped version of that image with the homography matrix, and I apply the LOFTR to get the matching points with the confidence, and I filter the key points with the threshold to get the best result and to neglect and avoiding the noisy points. Then estimate the homography using the Rensek algorithm, and in corner transformation I define the source image corners and apply the uh, wrap the corner with the ground truth homography that I have initially in my dataset, and wrap the corner with the estimated homography. Then I compute the corner error, and based on that corner error, I compute the AUC score. This approach completely follows that explained in the paper of the LOFTR, and this is the result of this. Uh, I run this algorithm on the train and test combined dataset. I get mean corner error 0.16, and this is the AUC score on the different thresholds. In 0.01 pixel, I get 0.45%, and in 1 pixel, 99.74%, and in 20 pixel, 100% result. In the algorithm 7, I again utilized the pre-trained version of the LOFTR. Uh, Firstly, for each image pair, I run the LOFTR and get the matching point and filter the matching point based on the confidence, and computed the mean confidence and assign the pseudo level based on the confidence. Means if the confidence is greater than 0.9, then I set the level 1, otherwise 0. This is called the pseudo leveling. Then I use the same VG architecture, but in the instead of predicting the homography matrix, I modify it to predict the confidence score. Then I apply the training process with the mean squared error loss and apply back propagation, weight updates, and save the best model. Then I utilized trained VGG model for the score generation. For score generation, I make pairing similarly as I have explained earlier. for each image in the test dataset with the every image of the trained dataset and assign the label if they belong to the same subject. And I compute the confidence score. Then based on this confidence score, I normalize confidence score and compute the dissimilarity by using the two different approaches. One is the exponential decay, and is the in one minus the confidence of the one minus normalized confidence, and I get the same result by using both these techniques. So we can say that confidence also tells the similarity of the images. And in last, I compute the ER result, equal error rate result, and I get 43% EER rate. In the algorithm 9, I make the pairing same as I explained earlier, assign this label if they belong to the same subject, and pass through the LOFTR module, extract key point with the confidence, filter the matches by confidence, and compute the mean confidence. Then instead of training, I computed the dissimilarity score by using both the techniques. One is exponential decay, and another is one minus of the normalized confidence. And I will get this EER at 22.35% at the threshold this with the genuine genuine images 24,920 and imposture 57 lakh 72,217. In the algorithm 10, I use the same LOFTR module to extract the key point, filter the confidence, but instead of direct computing the dissimilarity or training the model, I estimate the homography with the Rensick algorithm and define the corner of the test images. Now I applied the estimated homography, and as a ground truth, I applied identity matrix homography because initially I don't have any ground truth homography matrix. So I consider the identity homography, then compute the corner error and save the corner error as the dissimilarity score, and run this all run this on all pairs available in the file and aggregate all corner errors and labels. Then based on this corner error, I compute the EER, and I get 12.01% EER at on the genuine of 24,000 and imposture 29 lakh, and on the 100 genuine and 14,000 imposture pair I get the 5.83 EER rate. Then in the last algorithm I utilize same LOFTR module to extract the key points with the confidence, filter the confidence, estimate homography using the Rensick algorithm, compute corner error, and everything, and then pairing, making the pairing from test to train, and assign the label one if they belong to the same subject. And in the next, I modify the same architecture of the VGG16 to accept the convolution, to accept the two channel input. And in the regressor, I modify the layers to predict the corner error. And then in the training phase, I I started the forward pass, computed loss, backward propagation, and updates. And this process continuously going on the whole data training data set and validated on the validation data set, and the checkpoints are saved if the validation loss improves. And the uh, for score generation, In in this process, I trained the model on the small subset of the data set and evaluated it on the large data set. In the training, I have only the 14,000 pairs, and in the testing, I have something data set in the lakh, lakhs number of the records. For the score generation, I use the train model on the to predict the corner error and save this corner error as the simulated score and compute the ER result. And I get this EER 36.97 and 36.95% EER rate on the different threshold. And this is the comparative different comparative result. First is the EER rate that I get using the trained VG16 on the pseudo labeling 43%, and if I trained it on the dissimulated score, then I get the 36% EER rate. And if I compute the dissimilarity direct from the confidence, then I get the 22% EER rate. And if I compute the EER score by estimating the homography and finding the corner errors between the estimated and the uh, uh, identity homography wrapping on the images, and I get 12 point and 5.83 EER rate on the different number of the images. And in conclusion, I generated the homography wrapped forehead images, trained the VG16 network, trained modified vision transformer to estimate the homography transformation, compute similarity scores like SSIM, cosine, Euclidean, and prepared a new ground truth dataset by extracting and annotating forehead creases region from the videos. Used pre-trained LOFTR to extract the dense matching key point with confidence. Estimated homography using the RANSAC. Generate the pseudo labeling. Compute equal error rate using the LOFTR based mean confidence to compute the dissimilarity matrix. Evaluated ER using the corner error, and build the complete image matching pipeline by combining LOFTR and VG16 for robust verification scoring. Thank you for watching.